Hello, this video is going to be a tutorial of how to conduct multi-level analyses using R. I'll go over the R code that is used, I'll also interpret some of the output produced, and I'll go over some general concepts behind multi-level modeling. The dataset that I'll be using is vaccination rates in New York City by zip code. And also the R code that I'll be using is the nlme package. So multi-level modeling. What it does is it allows us to account for clusters or groupings we might find in our sample. Now, what these clusters and groupings might be is, let's say you have a sample of students. These students might come from different classes or schools, or let's say you have a sample of patients. They might come from different hospitals, or they might have different nurses. So, and these are examples of different clusterings or groups that might impact some dependent variable you might be interested in some way. In that, let's just say you're interested in whether a patient recovers better based on some drug you use, and you suspect maybe some nurses might better aid people in their recovery, or let's say schools, and you're trying to measure performance on some tests, you might suspect that students from different the school might impact that in some way. And all multi-level modeling does is it allows us to account for this. Now you might be wondering, well, why can't I just fit my linear regression model on this sample instead and then just ignore it? The issue is that you might be violating assumption of linear regression, and that's independent errors. Now, this example that I really like that I was taught is, let's say you have about 10 different schools, and in each school you have 100 students. Altogether, you have a sample of about 1,000, right? So you might be thinking, oh, this is great. I have a very large sample, and let's say I'm trying to predict this achievement and what factors impact achievement in this math test. Math test is my dependent variable, and you're comfortable. You have this really large sample. Now, the issue is that you have 100 students in 10 different schools. And let's take this extreme example where each student within each school is perfectly correlated with each other. In this case, if student A and student B in the same school is perfectly correlated with each other, this means that you technically, your true sample size is the number of schools that you have, which is 10. So you don't have a sample of 1,000, you have a sample of 10. And you can no longer use it to, throw in all these independent variables you might be interested in. So to avoid this, you can use multi-level modeling. And it's not the only reason why you might be interested in using multi-level modeling. And that's basically what it does. It accounts for this between cluster variance, between grouping variance, like the variance between schools, and also accounts for variance within the actual school or cluster or grouping that you might be interested in. Now, other benefits to doing multi-level modeling is that you can also incorporate level 2 predictors into your model. So it allows you an opportunity to see another layer of information. So let's go over the actual data set that I'll be using. So first, I put it together. I pulled in data on demographics by zip code that I found from Kaggle. It provides general age, median age of by zip code, things like ethnicity, proportion, percentage white, median age, income. The vaccination rates I got from New York City, I believe Department of Health. I pulled it down as of some date, and it shows the rate of my dependent variable I'll be interested in is full vaccination, meaning someone has gotten pretty much both vaccinations, fully vaccinated. And this is by zip code. And in addition to that, I pulled in another data set. This one was from the Department of Health. It's basically looking at this is where I'm going to get the neighborhood names and boroughs. It's posted on New York City Department of Health. So Yeah, so first I already loaded these three files together. I downloaded them. I'll figure out some way to make it available for everyone. But for now, there was some manual work that I did because some of the information was just posted on the page. But I'll find some way to post it. So right here, I'm just going to do some quick data. I already loaded it, and you can see it already in my global environment. Now I'm going to do some data cleaning. I want to make sure all the zip codes are named the same. I'm basically changing this function right here allows me to change the name or rename a column so I can later merge it. And I'm merging vaccination rate using the merge function to merge vaccination rates with demographics and then vaccination rates with borough information and neighborhood name. Next, I will be taking a subset of the data set. The subset is only going to take the specific columns and variables or variables that I'm most interested in. So the function is subset, and this is the data set, and I will select only these variables. I'll quickly go over them. It's zip code, the percent fully vaccinated for that zip code, median age for that zip code, household income, percent white, percent college or above. The grouping variable is neighborhood, and I included an additional grouping variable, which I'll get to later, which is borough. Now my sample is zip codes within New York City, so it's not individuals, it's just zip code. And in New York City, there are 5 boroughs within New York City. Within each borough, there are a number of neighborhoods, and within each neighborhood, there are a number of zip codes. So I should have prefaced this by saying that this is not the best data set for this. I'm just mainly using this just to go over how to run multi-level modeling in R. You shouldn't draw any conclusions from this. This is not an ideal data set. Ideally, I would have the actual individuals who are eligible to be vaccinated, and then I can cluster it. My level 2 clustering would be zip code. But in this case, my level 1 clustering or my sample is made up of zip codes, and my level 2 clustering is neighborhood. So let's run this. And the data set is named VAC3 now. And we can view it, but I already went over it. So I'm specifically going over significant factors that impact the vaccination rate of a zip code. And my grouping variable is neighborhood. And it's mainly for just demonstration purposes. So let's run a regular linear regression model on the sample of zip codes, ignoring the grouping of neighborhood. So to do this, you use the nlme function, and you basically name percent fully is the name of our y variable or dependent variable. Then you just enter this tilde, and you enter each independent variable you're interested in. This is a multiple linear regression model. And I'm going to name it mod1. Let's run it. And now let's quickly look at the output. So right here, we can look at the coefficients, and we can see for each variable, which ones are significant or not. And we can see right off the bat, we have 2 significant predictors among the set of variables that I included, and that's median age and percent college or above. And this is without taking into consideration the nesting or grouping variable. So let's try and account for it. And the package I'll be using is nlme. Let's call it. So, okay. So yeah, so one thing to note right over here. What I'm doing right here is to run the multi-level model, you use the nlme function. So you set your fixed variables, This is the ones that you want to remain consistent, and random. What multi-level modeling does is it breaks this apart. It allows your random intercept to vary across groups. So your intercept is going to be the mean of your dependent variable when all the other values, or when all the other independent variables are 0. And we're just going to let it vary across groups. And so, and also, this is the name of the data set, and it's not, I don't believe it won't run on unless I say ignore all missing cases. So for now, we're just ignoring everything that's missing. And the reason why I'm running the null model, this is why it's a null model, is that it includes no other independent variables. It's just the dependent variable, which is fixed, and a random intercept. So let's run it. And let's look at the results here. So first thing, it'll give you the relative fit indices right here, and it's using restricted maximal likelihood estimation. And here's the formula, and it gives you the fixed effects, and I just have, there's no independent variables, just the intercept. I call this the null model. And here's the, I scrolled over it, but here's the random effects. This is the intercept standard deviation across each of the groupings. And this is, so you can think of this as the between standard deviation, and this is the within. Now, the first thing you have to do is, do we even need, or the first question you have to ask, do we even need to run a multi-level analysis? And to check to see whether you should be running it or not, you need to look at your interclass correlation. This looks at the variance that's accounted for by your grouping variable, in this case neighborhood. If it meets some threshold, then you're justified in running the multi-level model. If not, then you can just ignore it and just run your linear regression model. So let's look at the interclass correlation. And now the interclass correlation is going to be the variance, which is this squared divided by this squared plus this squared right here. And fortunately, there's a function within library psychometrics that will allow you to just do it. So to run it, this is the name of the function, icc1.lme. This is your dependent variable, your grouping variable, and your data set, and that's all that's needed. And I'm just going to name it. Why did I do that? Edit, undo. So that was an accident. Okay, let's just run it. And I named it ICC, so when I call it, it'll give me the value. So it's about 40%. So what this means is 40% of the variance in the model can be accounted for by neighborhood. Now, in other words, and you can subtract 1 minus the ICC, and that'll give you pretty much 60% of the variance is accounted for by the within subject difference, or within within the grouping of neighborhood, which is zip codes. Now, oh yeah, and here's the formula right here. I just this is if you just wanted to calculate it without using the function. But the key thing is that the ICC is higher than 0.1. That's generally recommended. So if you see anything higher than 0.1, then you're justified in running a multi-level model, and you shouldn't run the linear regression model. So next thing you might want to do, or you might want to consider doing, is centering your variables. So why you might want to center your variable is that it makes the intercept value interpretable. In addition, it also gives you an opportunity. It also accounts for, helps mitigate issues of multicollinearity. Also, like if you have a level 2 variable, that you want to include that's somewhat related to your level 1 variable, which I'll go over. So there's some advantages to centering your variable. And what is centering? You're just taking your independent variable and subtracting it by the mean. Now, there are two types of centering, group and grand mean centering. Group mean centering means you are subtracting the basically the mean of that group or that clustering from each individual participant, in this case zip code. So for each, in this case, so neighborhood, I will calculate a mean for each neighborhood and I'll be subtracting it from that group. So a 0 would mean that a value of 0 would mean that the zip code has, let's say, the average amount for that independent variable within that group, not taking into consideration the other group. Now, grand mean centering is the more basic one, where you're just taking the mean of all the entries across all groups. Now, if you have level 1 and level 2 predictors, you might want to use your only option is to use grand mean centering for a level 2 predictor. That's if a level 2 predictor or independent variable is something like a characteristic of neighborhood that you're including that is aggregate. Let's think of it as an aggregate across zip codes for a specific neighborhood in this specific example. Or another case, like let's say you have students as your level 1 and school level 2. Level 2 predictor would be a characteristic of school, like private versus public. That would be an example. And the advantage of multi-level modeling, you can include this. And in this case, if you have level 2 predictors that you might want to center, let's say a continuous example of school is like the average achievement within that school. You won't be able to center within group anymore. You have to center it, use grand mean centering instead. So to do that, so for in this case, I'm just going to do group mean centering, and basically it depends on your data. You have to make a decision on whether it makes sense for your data or not to do it. One thing I forgot to just load is the dippler, because I'm also using functions like this. Let me call both tidyverse and dippler. And right here, what I'm doing is I am grouping by neighborhood and using group underscore by, and then using mutate to calculate a mean for each group across the zip codes part of that group, which is neighborhood. And this is just basically pipe text. I'm basically doing one function after the other, and ultimately with ungroup, I'm just putting it back into the original data set, which is VAC3. And let me just run everything together. It's saying, well, it's some issues because I have some missing data, which I'm going to ignore when I run the model. So now I have a column that is estimating the mean for each group. To get the group mean, I just have to subtract the value. So what I'm doing is, for example, median age right here, to get this is the group mean centering of median age for a specific zip code. I am subtracting the median age, the specific value, from, I'm subtracting the mean, the group mean right here, that I basically calculate from that specific value. And I'm doing this for all the independent variables that I'm interested in. And again, the reason why you might want to do this, it should be based on the data. Don't feel like you have to do this group mean centering. And now that I group mean centered all my independent variables, I'll fit my multi-level model. Again, using the nlme function, the fixed variables are the dependent variable and all the independent variable. The only thing allowed to vary across groups are intercept, meaning that there's a specific different intercept for each group. Now, let's look at the summary for Mod 2, which is my multi-level model. So let's scroll up. So again, that's the standard deviation by random effect. But now let's look at the actual fixed effects now that we have some independent variables in it. So the value 5.99, the intercept, or 6 rather, is the average percent fully vaccinated across zip codes when all the other independent variables are 0 or at their group mean. So 6%, and this is accounting for the variability between as well, because this is a multi-level model. And we can interpret the slopes or the independent variable as, like, for example, right here, median age. The median age would increase right here. It's a positive impact by 0.34 for every 1 year older, 1 year increase in median age for a specific zip code over the group mean for that zip code. So, and what we can see here is that all of the variables are significant except this one right here, median household income. So we're able to, by accounting for this variability, we're able to find more predictive independent variables from our model. So next, what I'm going to do is the next model I'm going to run is going to include a level 2 predictor. Before, all the predictors were level 1, meaning they were specific to the zip code with my level 1. But now I'm going to include a level 2 predictor, which is specific to the actual grouping variable, in this case, neighborhood. And what I'm going to do is now take the grand mean. I'm going to grand mean center. I'm going to take the aggregate median age by neighborhood, which I previously calculated, and I'm going to center it. I'm going to subtract it by the overall mean, value. The overall mean for median age 2, which was the aggregate median age by neighborhood. And I'm going to create this new variable. I'm using the scale function. Center is equal to true, scale is equal to false. And now I'm going to include it. And the thing is, I'm going to name it mod 3, my third model. And I'm just going to include it. It's going to recognize automatically that it's a level 2 predictor. I'm just going to run this and then look at the summary. And now let's look at our independent variables. And you can see it recognizes that median age to underscore 2c. Our level 2 predictor is level 2 because of the degrees of freedom right here. It's based on around the neighborhood, the number of neighborhoods, as opposed to the other ones which are based around the number of zip codes in my sample. Now, yeah, so yeah, and this is a really great feature of multi-level modeling is that you can include these sort of characteristics. In this case, you find that it's significant. So that and an important part right here is, I'm sorry, I almost forgot to say this, is that level 2 predictors are only used for the level 2 groupings, meaning that when I'm interpreting right here, a significant variable would mean that it's a significant predictor of the neighborhood vaccination rates, not necessarily zip code. You can't use level 2 1 predictors to make conclusions on anything that's on level 1, and you can't, and vice versa. You can't do that either. Meaning I cannot say that the median age of the aggregate median age level 2 predictor on the neighborhood is a significant predictor of a specific zip code vaccination rate. So that's the one thing I avoid. So it's significant, but it's a significant impact on the neighborhood mean vaccination rate. And this is, I forgot to go over this previously, it also gives you correlations across the intercepts and the variables you included. And yeah, and this is the distribution of the actual standardized within group residuals. And you can always check. This also gives you like some descriptives of my sample size, which is pretty small, and the number of grouping variables that I had, which is 42. Now I want to run one more model, or this is this is going to be the penultimate model. It's going to be another model after this. Now let's say you weren't particularly interested in adding a little to predictor. Here is what I'm adjusting now is not only am I letting the intercept vary across groups, but I'm also allowing a specific slope to vary across groups. What this means is that what I'm saying here is that the impact of median age on my dependent variable, which is percent fully vaccinated, median age of a zip code, the effect of median age on a zip code on percent fully vaccinated varies across groups, and not just the intercept, but also the slope. And the reason why you might want to do this is basically it's only if you have a grounded or strong theoretical reason why to let the slope as well as the intercept vary as well. But let's run it. Let's take a look at the model. And you can see one thing that changes when you look at the random effects is that you get the correlation as well. You get the standard deviation for the actual slope as well, which right in this case is 0.345, along with the standard deviation for the intercept, and this is within. It all gives you the correlation. It's the correlation between the intercept and the slope that I included. 0.82, a high positive correlation would indicate that as the intercept mean increases, you would also expect the slope to also increase as well. Now, scrolling down, we can look at whether this impacted anything or not. And the first thing we can immediately see is one of the predictors is no longer significant. Right over here, percentage white is no longer a significant predictor. I should have said this earlier, but a significant p-value would be 0.05 or lower. And it would indicate this via, the asterisks are not included in this one, but yeah, so it was, when I didn't let slope vary across groups, it wasn't, it was significant, but now it isn't. So so what you might be wondering, why should I let the slope vary? It's suggested that one suggestion is that if you feel that for some reason, let's just say it's some nuisance variable of some sort, it's like the grouping variable is not something that you feel is going to make a strong impact and it's just there, then you may not want to also include a random slope, but there should be some theoretical reason why you want to do so. But let's further examine this, like this median age by percent white, just to look at the data itself. Let's run a quick correlation between these two, and we could have also looked at the correlation provided in the previous output, but this using the function core.test lets us look at median age and percent white. And we see there is a significant correlation. So the older the older zip codes with a higher median age tend to have higher percentages of white people, or people reporting the ethnicity of white. Now, you might also want to compare models. You can use the ANOVA function to do that. You just have it's ANOVA and the two names of the model. This is Mod 2 was the model with all the independent variables, and the multi-level model with all the independent variables, and Mod 4 was the last one I ran, which allowed the intercept and slope to vary. And we can see that the latter, Mod 4, where I allowed the intercept and slope to vary, improved the fit significantly. Now, again, you should, for the most part, the indications that I've gotten is that it should be based on theory whether you want this slope to vary as well. And I'm like rushing right through it, but yeah, just one last quick thing is you might have an additional grouping variable, a level 3 variable. In this case, if you want to add it, this is the way to add it. And here it's borough. So like I said before, neighborhoods themselves are also clustered into borough. And like this is, I just wanted to show the code of how to run it. Oh no, I did not run it properly. Okay, so this right here, yeah, so all that's changed is now what's allowed to randomly vary. There are a couple of random effects now, and I specifically say the first allows the intercept to vary across boroughs, level 3, and the second allows the intercept to vary across neighborhoods, which is level 2. So yeah, this is how pretty much to run this level 3 analysis. And as before, here are the fixed effects and the correlations. So yeah, and it also gives you some descriptives as well. The number of groups, so there are 5 boroughs, 42 neighborhoods. So yeah, so let me know what you think of this video. I'm sorry I rushed right through. I'm like changing from room to room. But let me know what you think. Also, again, I should have stated this at the beginning, I'm not an epidemiologist. You shouldn't take any the results that were found here to this data set is not the best. It's best if I had individuals and only individuals that were eligible. In addition, I'm only selecting a specific number of independent variables. Once you throw one thing and an additional thing to model, anything can change. And that's pretty much it. I hope you liked it. Let me know what you think.